Good evening. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. A very good evening and welcome to week 4 of the online sessions for the course on computational science and engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So for the past couple of weeks, we have been looking at ordinary differential equations, and there is just one last method which is left. And as regards the contents for this week, uh, mostly the transforms such as Fourier transform and Laplace transform were covered in the lectures, as well as maybe some say preliminary treatment of partial differential equations. And when I looked at the assignments, I saw that there was a good chunk of questions on Laplace transform. So maybe that is some aspect which we will focus on today for the most part. After we are done with this last remnant topic from ODs, which is on the method of variation of parameters. So if we just recall, uh, second order differential equation in standard form is given here to us, y double prime plus px times y prime plus qx times y equals f of x. Now this is a non-homogeneous equation because its RHS is not 0, and so the general solution, say, so y will have two parts. It will first have a complementary function, which is actually the solution to the homogeneous part. And it will also have a particular solution. We denote these by yc and yp respectively. And we know that the particular solution, so typically if the homogeneous solution is say some c1 y1 plus c2 y2 for a second order ODE, we know that the particular solution in this case will be some combination of these two solutions. It will not be a linear combination because the terms will also have other functions of x multiplied with these solutions. So the particular solution as shown will be some function u1, which is a function of x times y1, plus some function u2 of x times y2. Y1, y2, as we just saw, constitute the fundamental set of solutions of the associated homogeneous form. That is, when we put RHS equal to 0 and solve this equation, we obtain the complementary function containing these two solutions. And after some algebraic manipulation, which involves differentiating this form of the particular solution twice, and after some clever rearrangement, what we can do is we can obtain these functions u1 and u2. So just to recollect, our particular solution consisted of u1 y1 plus u2 y2, where u1 and y2 are functions of x, and y1 y2 are from our complementary function c1 y1 plus c2 y2. How do we determine these two functions that give us the particular solution? Well, the algorithm is outlined right here. We can obtain their derivatives from these two Wronskians. So u1 prime is equal to w1 by w, and u2 prime equals w2 by w, and what each of these Wronskians are is also outlined here. So w is the Wronskian of y1 y1 prime and y2 y2 prime, and as we remember from our previous week's discussion, Wronskian is analogous to determinant. So say this Wronskian will come out to be y1 y2 prime minus y1 prime y2, and so on. For the Wronskian w1, we simply replace the first column of the determinant with 0 and fx, and for the Wronskian W2 we replace the second column with 0 and fx. Fx again being the RHS of our original second order differential equation. So I mean, if I were to just outline all these steps together, the first step is finding the complementary function. Typically denoted as y of c, and this yc will come out to be some linear combination of y1 and y2. We have these two solutions for a second order ordinary differential equation. C1 and C2 are some constants. In the second step, using these functions from the complementary solution, we compute. So use y1 and y2 to compute the particular solution, which will have the standard form u1 y1 plus u2 y2. The only difference being in this case u1 and u2 are not constant, rather they are functions of the independent variable, typically say x or t, whatever you are dealing with. And in the third step, we finally get the general solution, which will be just a linear combination of the complementary function in the particular solution. So as you saw, we are actually, to find u1 and u2, we are actually seeing what we are getting directly are u1 prime and u2 prime, or the first derivative of the two functions. So we will integrate them to get our original functions u1 and u2. This will be an indefinite integral, and some constants of integration will enter the picture. What happens to them? So I've included this small section which outlines or tells us what is really happening. So say if you did include those, so say for example you had you obtained u1 prime from the two Wronskians, and then you integrate it to obtain u1, and that will give you something like, say, the integral of u1 prime if the independent variable is x, equals some u1 of x plus some constant a1. Similarly, some u2 prime dx will give you some function u2 of x plus e2. And if we substitute it back into our general solution, which is y, we see that they are absorbed into the constants c1 and c2, which were coming from the complementary function. And thus we have these new constants, capital C1 and capital C2, associated with the complementary function. And so while we are doing this indefinite integral to obtain our function c1 and u2 from their derivatives, we need not really add constants of integration, because in the grand scheme of things they are being taken care of anyway. And previous another method which was discussed and which you might be familiar with is the method of undetermined coefficients, where you look at the general form of the RHS function, say f of x, and then you try to guess a solution based on that general function. So say if on the RHS you have something like a sine of x, you start by assuming the particular solution to have a function like say some c1 sin x plus c2 cos x, because you know that its derivative will the derivative of sine will be cos, the derivative of cos will be minus sine, and so on. Or if it is some other exponential function, you assume that a particular solution will also have some constant times uh, uh, an exponential function, and so on. And typically standard tables are available that help you predict or guess the form of these solutions. However, the method that we just discussed here, called the method of variation of parameters, offers some distinct advantages over this method of undetermined coefficients. Yeah, just take a minute to list them down here. So comparison of method of variation of parameters. It's the method of undetermined coefficients. So the method of variation of parameters always, it's a very strong word, but it does always yields a particular solution will be. Of course, the solution should exist, and the condition for that is provided the associated homogeneous equation can be solved. Because as you saw, to obtain the particular solution, we must first have our complementary function, which will have those two solutions to the second order ordinary differential equation y1 and y2, and so the equation should be solvable in the first place. Second, it has been seen that this method of undetermined coefficients is limited to cases where the input function is of some elementary types, or says a combination of a few types of elementary functions. Say such as ones involving constants or polynomials or trigonometric functions. Or exponential, as we discussed. And thirdly, this method of variation of parameters is not limited to ODEs with constant coefficients only. And so it is better equipped to handle a larger gamut of say ODEs which one might encounter during their research. And the previous section say familiarized us with ordinary differential equations of the second order, but we also have the same formulation of the method of variation of parameters for any general nth order differential equation, and we'll just briefly touch upon its algorithm. Maybe we'll even solve a question in the tutorial. So, say for the linear nth order equation of the form the n derivative of n plus pn minus 1 times the n minus 1 derivative of y plus p1 times y prime plus p0 times x, p0 times y equals f of x. Again, assuming this can be solved, or the homogeneous part can be solved. So assuming that a solution exists, for the homogeneous part of this, so the n derivative of y plus some pn minus 1 times the n minus 1 derivative of y plus p1 times y prime plus p0 y equals 0. The solution, as we know, will be called the complementary function and will have some general form like c1 y1 plus c2 y2, and for an nth order it will have n terms, uh, n such functions. So Cn minus 1 yn minus 1 plus Cn yn. If this complementary function exists and can be found, then a particular solution will similarly be u1 y1 plus u2 y2 plus un yn, where in this case these u's are not constants like they were previously. They are indeed functions of the independent variable, which in this case is x. And so again we can have this matrix of equation given by 9, and utilizing Cramer's rule we can again obtain the derivatives of each of these functions and can integrate them back to obtain the functions themselves. What those Wronskians will look like has been illustrated for a third order linear differential equation, and here we see that again the Wronskian W is just consists of the functions, solution functions and the derivatives. So y1 y1 prime, y1 double prime, similarly for y2 and for y3. The Wronskian W1 consists of changing or replacing this first column with zeros, and just in the last row you have fx. W2 will involve replacing the second column with zeros with fx in the last row. Similarly, W3 will have the third column replaced with zeros and fx in the last row. We will also solve some of these questions or some ODEs by this method of variation of parameters, and that'll make it more familiar and make the things clearer. Of course, in any examination or in any, say, practical world problem which you encounter, you will have your own choice of the method which you want to use. No one will really restrict you saying, say, solve this particular problem by a given method, but then you have to choose the one which is more suitable or the one you are familiar with. Okay, now let us talk about Laplace transforms. And the idea of transforms might appear alien, but we have been dealing with it for quite a long time. And let us understand it like this. So say we have been given some function say square. Now x square, as we can see, is a quadratic polynomial. If we take the derivative of fx with respect to x, we get x, which is 2x, which is a linear function. If we integrate fx dx, and this is an indefinite integral, we will get x cubed by 3 plus some constant of integration. Now this is a cubic polynomial. And if we were to integrate fx with respect to dx over some chosen interval, say 0 to 3, then what we will have is by 3 evaluated at 0 and 3 becomes 27 by 3 minus 0 or 9, which is just a constant. So depending on what operation we perform on a given function, we change the type of the function. Like we were given a quadratic polynomial initially, and when we differentiated it, we got a linear function. If we integrated it in an indefinite integral, we got a cubic polynomial, and in a definite integral, we got a constant. We have transformed this function into something else. And one of the more useful transforms is something called a Laplace transform. And here is the formal definition of the same. So let f be the function that is given to us, and let it be a function which is defined for time t greater than equal to 0. And then the Laplace transform of this function f of t is formally defined as the definite integral from 0 to infinity e power minus st f of t dt. When we are this when we are evaluating this integral, and when this integral converges, if at all, the result is a function of s. Originally we started with a function of t, f of t, and the evaluation of this integral will give us some function f of s. So in fact, we changed the domain. Originally we were working in the t domain, now we have ended up in the s domain. And the way to distinguish these two is by changing the case. So if your original function was a lowercase, such as in the example given here, your Laplace transform is typically denoted by an uppercase letter, but it can be reversed also. Like if your original function was given with capital letters, its transform can be denoted with a small letter also. But what is important is to keep the distinction between the two and have a consistent notation. For example, here the Laplace transform of capital H of t can be denoted by small h of s. For more mathematical rigor, we'll also look at the conditions for the Laplace transform to exist. So if ft is a piecewise continuous function on the interval 0 closed uh, infinity and of exponential order, so there are two conditions here: piecewise continuous on this interval, and if it is of exponential order, then the Laplace transform of the function f of t exists for s greater than c. What is c? For that, we need to see what is meant by this second condition, or if that the function has to be of exponential order. Now, any function f is said to be of exponential order if there exist constants c and m both greater than 0, and for some capital T greater than 0, such that the magnitude of the function f of t is less than equal to capital M times e power ct for all t greater than this chosen capital T. And it is illustrated here in the figures to the right. So if we look at figure 4.112, we have this function f of t given to us, and we have this other function which is capital M times e power ct. Now below t less than capital T, we see that our function is greater in magnitude than this capital M power e of ct. In this region, our function f of t is not of exponential order because it must be smaller than or equal to. However, after t, we see that the function capital M power e of ct overtakes this in magnitude, and so for all t greater than capital T, our given function is of exponential order. And in the figures to the right, we also have a few examples, and in all of these cases, functions with the blue graphs are of exponential order because they are, in every case, they are smaller than a function which is of the general form capital M power e power ct. Please allow me a minute, I'll just have a sip of water. Now, while the formulae for some standard Laplace transforms might already be familiar to you, or they are always readily available in standard textbooks, I have just outlined a few of the most common examples here to give us a good starting point, and we can refer back to these when we are solving the exercises. The Laplace transform of 1 is 1 by s. The Laplace transform of t power n is n factorial by s power n plus 1. The Laplace transform of e power at is 1 by s minus a. Laplace transform of sin kt is k by s square plus k square, and of cosine kt is s square by s square, s by s square plus k square. We also have the transforms for the hyperbolics. So sin hyperbolic kt when transformed becomes k by s square minus k square, and the Laplace transform of cos hyperbolic kt is s by s square minus k square. Again, the Laplace transform is a linear transform, as in if you have to find the transform of f of t plus g of t, then this is the same as finding the Laplace transform of f and t and the Laplace transform of g of t separately, just adding them together. Again, even if you multiply these functions with some scalars, say now you're asked to find the Laplace transform of some alpha times f of t plus some beta times g of t, where alpha and beta are scalars, it simply becomes alpha times Laplace transform of f of t plus beta times Laplace transform of g of t. And this can easily be seen by computing the relevant integrals. So now let us reinforce these concepts by just finding the Laplace transform of a very simple function, something like sine 2t. The formula for which is already available to us, but we would like to double check and perform the integration ourselves uh, and see what we end up with. So just for remembering sake, I'll just write the general integration form of the Laplace transform. Laplace transform for any function f of t for t greater than or equal to 0 is equal to the integral from 0 to infinity e power minus st f of t times dt. And so let us now try to find the Laplace transform of sine of 2t. So as usual, this will be integral 0 to infinity e power minus st, the given function sine 2t dt. And we have a product of two functions. The way I remember this is, say if I have to calculate the integral of a product of two functions, say both are functions of x, this becomes u into integral of v dx minus integral of differential of u into integral of v dx. And the whole of it is also multiplied by, I mean, you have to take the integral of the whole with respect to dx. What if we are calculating definite integrals, something like some a to b uv dx? Then the product of this first term combined is to be evaluated between a and b, and this outer integral becomes a definite integral while the inner one still remains indefinite. And so let us now use these formulae to solve or arrive at the Laplace transform of the given function. So just for convenience sake, I will pick u equals sine 2t and v equals e power minus st, and see where this leads us. So if I were to denote this integral as just I, then using our formula for the product of integral of products, this will give us u integral of v dx, or in this case t, minus integral of Oh, sorry, not here. This entire function is to be evaluated between 0 and infinity. As integral of differential of u, so d dt of sine 2t times integral of e power minus st dt whole times dt. And now let us try to solve this step by step. So this is sine 2t. E power minus st dt is simply e power minus st by minus s, and we have to evaluate this product between 0 and infinity. For this other part, this will become d dt of sine 2t is 2 cos 2t, and this again becomes e power minus st by minus s dt. And when we are trying to evaluate these terms, so say for this first term, when t equals 0, sin 2t becomes 0, and so the whole term goes to 0. And when t tends to infinity, sin 2t is still finite. Whereas this second term, e power minus st, goes to 0 because t is very large. E power st becomes very large, but 1 by e power st, that is e power minus st, becomes very small. If t tends to infinity, e power minus st tends to 0. So this entire first term becomes 0. Only the second term survives. And the second term is e power minus 2 by minus s is 2 by s times integral 0 to infinity cos 2t e power minus st dt. And let us just denote this integral by some other notation, say I1. So we started trying to solve one integral and we ended up with another. Let's see where this leads us. So again, we are trying to solve this integral I1 now, which is simply integral 0 to infinity cos 2t e power minus st dt. Again, as per our product rule, we take u equals cos of 2t, v equals e power minus st, and then I1 becomes u into integral of v dt minus integral of v dt of u times integral of v dt whole time dt. This becomes cos 2t and e power minus st by minus s evaluated between 0 and infinity minus integral 0 to infinity d dt of cos 2t is minus 2 sin 2t, and this integral is again e power minus st by minus s dt. Now again, let us try to evaluate this first term. When t is equal to 0, cos 2t is 1 and e power minus st by minus s becomes simply minus 1 by s. And when t is tending to infinity, cos 2t is still finite because its value will always oscillate between minus 1 and 1. But this other term, as we saw, e power minus st by minus s tends to 0. and so their product will also tend to 0. Thus what we'll be left with is 0 minus 1 by s and minus 2 by s equals 0 to infinity sin 2t e power minus st dt, or this becomes 1 by s minus 2 by s integral 0 to infinity sin 2t e power minus st dt. And we have in fact ended up with the very integral that we started to evaluate. And since we were denoting this integral with I, right, I1 equals 1 by s minus 2 by s times I. This is one of the equations. We also have another equation here, if you remember. We wrote that I equals 2 by s I1. Let us substitute the value of I1 here, and then we will have an equation in I, which hopefully we can solve and finally find the Laplace transform for this function sin of 2t. So I equals 2 by s times 1 by s minus 2 by s times I, which is 2 by s square minus 4 by s square times I. Implies that I times 1 plus 4 by s square equals 2 by s square, or I times s square plus 4 by s square equals 2 by s square, which gives us I equals 2 by s square plus 4, and I have eliminated s from both sides, assuming s is not equal to 0, or perhaps the far more familiar form 2 by s square plus u square. Thus, the Laplace transform of sin of 2t becomes 2 by s square plus 2 square, or more generally, the Laplace transform of any function sin at equals a by s square plus s square. Again, remember this is the formula that we already saw. Just like we have the Laplace transform, we also have the Laplace inverse transform. The Laplace transform allows us to traverse from the t space or the t domain to the s domain, and the inverse Laplace transform allows us to come back from this s domain to the t domain. And on the surface of it, you are just if you know what the transform looks like, or if the transform is a very standard function, you already remember what the original function looked like. For example, the Laplace transform of 1 was 1 by s, so the inverse Laplace transform of 1 by s is 1 as given here. And so for the others, again very interesting to note that even the inverse Laplace transform is a linear transform. So whatever properties we saw, such as the Laplace transform of alpha fs plus beta gs equals the alpha times the Laplace inverse of fs plus beta times the Laplace inverse of gs. And now let us quickly solve one example of this inverse transform to ensure that we have absorbed this concept well. This is, we are asked to find the Laplace inverse of s square plus 6s plus 9 by s minus 1, s minus 2, s plus 4. We also involved, we also saw some similar functions last week, and we had a great time breaking them up into partial fractions. So let us do that again. And as we are well aware, any such function such as s square plus 6s plus 9 by s minus 1, s minus 2, s plus 4, which has this non-repeating factors, which has been factorized into non-repeating factors, in fact, can be represented as a by s minus 1 plus b by s minus 2 plus c by s plus 4. In each case, the order in s of the numerator is 1 less than the denominator. So say if I had some factor which had some square term, some s square plus 4, then the numerator would have been something like cs plus d. Okay, and now we have to find these numerators or coefficients. Now typically I've seen people do is they will multiply this out, obtain three equations in three unknowns and then try to solve them. But that can become very tedious. Uh, but we are smart, so we will learn something called a cover-up method. No, we are not really covering up any deficiency in our mathematical rigor. This is the actual name of the cover-up method, and why you will see shortly. So what we can do is, say we want to find a. Let us then multiply both sides of this equation by the denominator of a, which in this case is s minus 1. Multiplying with s minus 1 on both sides. Now we can in fact eliminate from both sides. I mean, it will cancel out wherever s minus 1 was already existing in the denominator. Now, in this equation, if we put s equals to 1, so what we are trying to do is really evaluate at s equals 1 equals a plus, see that when we put s equals to 1 in the second term, it goes to 0, or b by s minus 2 times 0, and so for the third term. So essentially what we have done is, in one single step, we have evaluated a, and what this is like is your original function I want to find the first coefficient, so I hide or cover up this first factor and evaluate this function at the first 0. This will give me a, and that in fact is 1 plus 6 plus 9, 9 plus 7 is 16, 5, 1 minus 2 is minus 1, 1 plus 7 minus 5, or minus 16 by 5. If I want to find b, I will simply cover up this second factor and evaluate this function, and then second 0 is equals to, and let's see what that gives us. 4 plus 12, 16 plus 9, 25 by 6. And if I want to find c, it's the same routine again. I'm now covering up this third factor and evaluating this function, and the third 0, which is minus 4, and that gives me 16 minus 24 is minus 8 plus 9 is 1 by minus 4 minus 1 is minus 5, 7 times minus 6 is 30. So what we have done is we have found we have found three coefficients. So s square plus 6s plus 9 by s minus 1, s minus 2, s plus 4 can indeed be written as the sum of these partial fractions being minus 16 by 5 by s minus 1 plus 25 by 6 by s minus 2 plus 1 by 30 by s plus 4. And so when I'm trying to find the linear inverse Laplace transform, what I'm simply doing is finding the inverse Laplace of each of these terms separately and then adding them together, as we saw from the property of Laplace transforms and inverse Laplace transforms. In fact, we can even pull the constants out. So minus 16 by 5 Laplace inverse of 1 by s minus 1 plus 25 by 6 Laplace inverse of 1 by s minus 2 plus 1 by 30 Laplace inverse of 1 by s plus 4. And if you remember the formula, Laplace inverse for 1 by s minus a equals e power at. This will give us the inverse Laplace of s square plus 6s plus 9 by s minus 1 times s minus 2 times s plus 4 equal to minus 16 by 5. Here a is equal to 1, so e power 1t plus 25 by 6. Here a is equal to 2, e power 2t plus 1 by 30. Here a is equal to minus 4, e power minus 4t. And indeed, this is the answer that we are looking for. However, what is the real motivation for learning about these Laplace transforms? Or what is the usability of this in our present course? So Laplace transforms are in fact another way, or they provide another method of solving differential equations. Say your a problem is posed to you, typically an initial value problem, just like we were discussing last week, that you have to find some function y of t which satisfies a given ordinary differential equation and some initial condition, thereby making it an initial value problem. What we do is we apply a Laplace transform to both sides of this equation, and after application of the Laplace transform, suddenly you find that your ODE or your differential equation became an algebraic equation. And we have been solving algebraic equations since school, junior school in fact. So when we are given an algebraic equation to solve, we can solve it with much greater ease compared to a differential equation which we are still learning how to solve. So we solve this algebraic equation and then we obtain the function capital Y of s, which is in fact the transformed version of our original function of interest y of t. Once we have y of s, we simply apply the reverse Laplace or inverse Laplace transform and obtain the original function that we were looking for, y of t. And this is the real motivation for learning or reading about Laplace transforms. Of course, in this for doing this, we must know how to transform those derivatives, and so this useful theorem is given to us. The Laplace transform of the nth derivative of f of t is equal to s power n capital F of s minus Sn minus 1 f at 0 minus Sn minus 2 f prime at 0 till Fn minus 1 of 0. And what we see that all these initial values at t equal to 0, f of 0, f prime of 0 till Fn minus 1th derivative must be supplied to us at t equal to 0. Given this information, we can easily use Laplace transform to solve the differential equation. Here are some other useful formula available for us, such as the Laplace transform of t power n f of t is equal to minus 1 power n and the nth derivative dn dsn of f of s. We also have the convolution theorem, which Professor Day also discussed during this week's lecture, uh, being that if f of t and g of t are piecewise continuous on the domain 0 to infinity and of exponential order, if you remember what that is, then the Laplace transform of the convolution of f and g is equal to Laplace transform of ft times the Laplace transform of gt equals the product of fs and gs. And in fact, it is the convolution theorem which has been used to find the Laplace transform of integrals, that is the Laplace transform of the definite integral 0 to t f of tau d tau is equal to f of s by s. Some other useful theorems which may prove uh, handy later on, such as for the Dirac delta function, the Laplace transform of delta t minus t naught is e power minus st naught, and the Laplace transform of a periodic function with a period capital T is Laplace transform of f of t is equal to 1 by 1 minus e power minus s capital T, where again t is the period of this periodic function, integral 0 to t e power minus st f of t dt. And we will just take a very short break right now, and when we return, we'll use some knowledge that we have learned today to solve some exemplary problems. So let us meet after a short break. So, good evening and welcome back. Let us now solve some exemplary questions based on the contents that were covered in this week. In the first question, we are asked to solve the given ordinary differential equation using the method of variation of parameters. Since we have already discussed the derivation in depth, we'll simply get started with it. The given equation is y double prime minus 4y prime plus 4y equals x plus 1 e power 2x. As we know, the general solution y will have the complementary function and the particular solution. For finding the complementary function, we take just the homogeneous part. So y double prime minus 4y prime plus 4y equals 0. And we assume a standard solution. So let y equals e power mx be a solution. And this would imply that y prime is m e power mx and y double prime is m square e power mx. When we substitute this back into our original equation, what we end up with is m square e power mx minus 4m e power mx plus 4 e power mx is equal to 0. Now assuming e power mx is not equal to 0, because then we will just have a trivial solution y equal to 0, we can eliminate it or we can cancel it from the equation. M square minus 4m plus 4 equal to 0. So m square minus 4m plus 4 would equal 0. M square minus 4m plus 4 is simply m minus 2 whole square, which implies that m equals 2 and 2. So these are repeated roots. And we know that in the case of repeated roots, the first solution is e power mx or e power 2x. The second solution cannot be the same because else then we just has duplicate solution. So as we discussed previously, the multiplicity of x will increase by 1, and so the second solution is simply x times e power 2x, and this gives us the complementary function as c1 e power 2x plus c2 x e power 2x, and you can substitute it back into the given differential equation and verify. Now we start working on the particular solution, and by using the method of variation of parameters. So in the method of variation of parameters, we assume that the particular solution yp is of the form u1, which is a function of x times y1 plus u2, a function of x times y2. And if we refer back to the formulas, u1 prime is equal to the Wronskian w1 by w, and u2 prime equals w2 by w. Also, from the given formula, you can find what individually each of these Wronskians are. So w was y1, y1 prime, y2, y2 prime. In this case, y1 is e power 2x, y2 is x e power 2x, y1 prime is simply 2 e power 2x, y2 prime is e power 2x plus 2x e power 2x. If we solve this comes out to be power 2x times e power 2x plus 2x e power 2x minus 2x e power 4x e power 4x plus 2x e power 4x. So this is simply e power 4x. What about the Wronskian w1? Here we will replace this first column by 0 and fx. 0 fx is x plus 1 e power 2x. Second column remains unchanged. X e power 2x, e power 2x plus 2x e power 2x. First term is simply 0, so this is minus x plus 1 e power 2x times e power 2x is e power 4x. And then on second W2, in this case, we replace the second column with 0 and fx. First column remains unchanged, e power 2x, 2 e power 2x, 0 and x plus 1 times e power 2x. This gives us e power 2x times x plus 1 e power 2x minus 0, which is simply x plus 1 times e power 4x. u1 prime, as we remember, was w1 by w minus x plus 1 e power 4x, and w being e power 4x, so this is simply minus x times x plus 1. So u1 is then the integral of minus x square minus x dx. This becomes minus x cubed by 3 minus x square by 2, and remember, we are not taking the constant of integration because that is already been taken care of in the final solution. u2 prime equals w2 by w. Computed w2 as x plus 1 e power 4x and w as e power 4x. u2 prime simply becomes x plus 1, in which case u2 becomes integral of x plus 1 dx, which is x square by 2 plus x, and again no constant of integration. So our particular solution, which was u1 y1 plus u2 y2, becomes minus x cubed by 3 minus x square by 2 y1, which was e power 2x, plus x square by 2 plus x times x e power 2x. And if we just were to simplify this, minus x cubed by 3 x square by 2 plus x cubed by 2 plus x square e power 2x, which becomes x cubed by 2 minus x cubed by 3 is 3x cubed by 6 minus 2x cubed, so this becomes x cubed by 6 plus x square by 2 times e power 2x. And so the general solution of the given non-homogeneous ODE is y equals the complementary function plus the particular solution. So C1, what is y1 again? It is e power 2x plus C2 x e power 2x plus the particular solution x cubed by 6 plus x cubed x square by 2 times e power 2x. There's one more question on the method of variation of parameters, and let's also quickly solve this. So, since this is a non-homogeneous equation, the general solution, where we'll have two parts, the complementary function and the particular function. For finding the complementary function, uh, this is the solution of the function y double prime minus y equals 0. So again, let us start by assuming y equals e power mx is a solution, which implies that y prime is equal to m e power mx, and y double prime is equal to m square e power mx. We substitute this back into original equation to get m square e power mx minus e power mx is equal to 0 or e power mx m square minus 1 is equal to 0 or m equals plus minus 1. So we have real distinct roots, and this would imply that one of the solutions y1 is e power m1x, just x, and the other solution y2 is e power m2x or e power minus x, and thus the complementary function becomes c1 e power x plus c2 e power minus x. Now we must find the particular solution, and if you remember correctly, the particular solution is of the form u1 y1 plus u2 y2, where u1 and u2 are functions of x. This becomes u1 e power x plus u2 e power minus x. The Wronskian w will be y1 y1 prime y2 y2 prime, which equals e power x, its derivative is also e power x, and e power minus x as a derivative minus e power minus x. So e power x times e power minus x is 1 minus 1 minus 1 is minus 2. The Wronskian w1 will involve changing or replacing the first column of w, 0 and fx being 1 by x. So 0, 1 by x, e power minus x minus e power minus x minus e power minus x by x. And the Wronskian w2 will involve replacing the second column with 0 and fx. This is simply e power x by x. Now the function u1 prime is given by w1 by w, which is minus e power minus x by x divided by minus 2 or half e power minus x by x, and this would imply that u1 is equal to half times the integral of e power minus x by x dx. Similarly, u2 prime is w2 by w. w2 is e power x by x. W is minus 2. This simplifies to minus half e power x by x. So the function u2 becomes minus half integral of e power x by x dx. Now, one would easily notice that these integration or these integrals are not very easy to evaluate. In fact, these are non-elementary integrals. That is, there is no way to obtain a closed form solution for these two integrals, and that is okay. So the particular solution then becomes u1 y1 plus u2 y2, which is y1 z power x e power minus x by x dx, and y2 was e power minus x. And so the general solution of the non-homogeneous ODE is y equals the sum of the complementary function and the particular solution, which is c1 e power x plus c2 e power minus x plus e power x by 2 times the integral of e power minus x by x dx minus e power minus x by 2 times integral of e power x by x dx. And this is the solution that we were looking for. Okay, given the paucity of time, maybe we will not solve these simple Laplace transforms. Maybe that can be done as a home exercise, but what we are more interested in doing is finding the Laplace transform, inverse Laplace transform, then finally solving these ODEs using this Laplace transform method. So let us focus on those questions. Now we are asked to find the inverse Laplace transform of the function 2s minus 4 by s square plus s times s square plus 1. And as we know, this function 2s minus 4 by, and we further factorize into s times s plus 1 times s square plus 1, and this can be written as the sum of the partial fractions a by s plus b by s plus 1 plus the third factor is s square plus 1. So as we were discussing, the numerator must only have one order in s less than the denominator. So this will become cs plus d. If the denominator were a cubic terminus, the numerator would be a quadratic. So you would have something like a cs square plus ds plus e. Now, a and b can be found by the cover-up method. So a is simply s minus 4 by s plus 1 s square plus 1 evaluated at s equal to 0, which is the 0 corresponding to a. This gives you minus 4 by 1, so minus 4. B can also similarly be calculated. So this is 2s minus 4 by s times s square plus 1, calculated at s equals minus 1, which will give us minus 2 minus 4 is minus 6 by 1 plus 1 is 2 minus 1 by minus 2 or 3. But can we find out C and D using the cover-up method? No, it's not so straightforward. So we will have to multiply out the terms. So after multiplication and just retaining the numerator on either side, this becomes A times s plus 1 s square plus 1 plus b times s square plus 1 plus cs plus d times s plus 1. And let us expand this. This will become a times s cube s plus s square plus s plus 1 plus b times s cube plus s plus cs cube plus ds square plus ds square plus ds. And if we group these terms, we'll have s cube times a plus b plus c plus s square times a plus c plus d plus s times a plus b plus d plus a. And the LHS is 2s minus 4. Now if we were to compare the coefficients of s on either side, coefficients of parts of s on either side, we find that the coefficient of s cube is 0 on the LHS, and so it must be on the RHS as well. So a plus b plus c is 0, which implies that c is equal to minus a plus b. Both a and b are already known to us. A is minus 4, b is 3, minus 4 plus 3 is minus 1, so c becomes 4, 1. And if we compare the coefficient of s square, a plus c plus d is again 0, which implies that a is the negative of the sum of a plus c. A is minus 4, c is 1, minus 4 plus 1 is minus 3, so d is 3. And so what we have done is we found all these coefficients. So 2s minus 4 by s plus 1 s square plus 1 equal minus 4 by s plus 3 by s plus 1 plus s plus 3 by s square plus 1. And if we want to find the inverse Laplace transform of this LHS, s plus 1 s square plus 1 equal minus 4 times Laplace inverse of 1 by s plus 3 times Laplace inverse of 1 by s plus 1 plus the Laplace inverse of. Now this term can further be broken into s by s square plus 1 plus 3 by s square plus 1. So this is s by s square plus 1 plus 3 times Laplace inverse of 1 by s square plus 1. Now we know that the Laplace inverse of 1 by s is simply 1. So this is minus 4. Laplace inverse of 1 by s plus 1 is e power minus 1t. So this is 3 e power minus t. Laplace inverse of s by s square plus 1 square is the Laplace inverse of cos t or cos 1t, and the Laplace inverse of 1 by s square plus 1 square is simply sin t. And so this is the solution which we were looking for. Again, a similar question on the inverse Laplace transform. So if we have time, we can come back to it. But for now, let us solve some initial value problems using this Laplace transform method. So in the In this question, the equation given to us is dy dt plus 3y equals 13 sine 2t, and the value of y at t equal to 0 is equal to 16. So it's an initial value problem. Let us try solving this using the Laplace transform. To do that, we uh, take the Laplace transform of both sides of the equation. So the Laplace transform of dy dt plus 3y equals the Laplace transform of 13 times sine 2t, which is the same as the Laplace transform of y prime plus 3 times the Laplace transform of y equals 13 times the Laplace transform of sine twice t. Now, just to recollect, I will write the formula for the Laplace transform of derivatives here. So the Laplace transform of the nth derivative of f of t is equal to s power n capital F of s minus s power n minus 1 f of 0 minus s power n minus 2 of 0 minus n minus 1th derivative of f at 0. For this given case, this will imply s power 1. It will be confusing to write that. S times capital Y of s minus y of 0. We only have two terms because we are dealing with a first order differential here. Plus 3 times y of s, because the Laplace transform of y of t is simply capital Y of s. That is in fact the function that we are looking for. Equals the RHA 13 times the Laplace transform of sine 2t will be 2 by s square plus 2 square. And we can multiply it out. This will become 26 by s square plus 4. The value of y at 0 is also given to us. So this equation further becomes y of s times s plus 3 minus y at 0 is 6 equals 26 by s square plus 4. Which implies that y of s times s plus 3 is equal to 26 by s square plus 4 plus 6, which equals 26 plus 6s square plus 24 by s square plus 4. And finally, this will imply that y of s 26 plus 24 is 50. 6s square plus 50 by s plus 3 times s square plus 4. Again, we must decompose this into partial fractions to be able to proceed. So let us do that. 6s square plus 50 by s plus 3 s square plus 4 can be broken down to partial fractions. A by s plus 3 plus bs plus c by square plus 4. We can easily calculate A by using the cover-up method. Let us do that. So A is simply 6s square plus 50 by s square plus 4 calculated at s equals minus 3. And this will give us Plus 3 square is 9, 9 times 6 is 54, plus 50 is 104, 5, 9 plus 4 is 13. Is this divisible? Yeah, so this comes out to be 8. For finding B and C, we must multiply out the terms. And if we retain only the denominator, 6s square plus 50 equals a times s square plus 4 plus bs plus c times s plus 3. This will become a square plus 4a plus bs square plus 3bs plus cs plus ac, or 6s square plus 50 equals s square times a plus b plus s times 3b plus c plus 4a plus 3c. Now we must compare the coefficients of powers of s. A plus b equals 6 because the coefficient of s square on the LHS is 6. A is already known to us and it is 8. So b becomes minus 2. And the coefficient of s on the RHS is 3b plus c. But on the LHS it is simply 0. So c becomes minus 3b, which is 6. And so we have found the coefficients for the partial fractions. 6s square plus 50 by s plus 3 s square plus 4 equals is 8 by s plus 3 plus b is minus 2s plus 6 by s square plus 4. And this is equal to y of s. Y of t, the original function that we are looking for, is the Laplace inverse of y of s, and so y of t is the Laplace inverse of eight by s plus 3 plus minus 2s plus 6 by s square plus 4, which is 8 times Laplace inverse of 1 by s plus 3 minus 2 times Laplace inverse of s by s square plus 2 square plus 6 times the Laplace inverse of, or maybe a cleverer way to write this would be 3 times Laplace inverse of 2 by s square plus 2 square. And now since we are familiar with the formula, we can directly write these transforms or these inverse transforms. The first one is simply e power minus 3t. This s by s square plus 2 square is simply the Laplace transform of cosine of 2t, and 2 by s square plus 2 square is the Laplace transform of sine of 2t. And this, the solution that we are looking for, y as a function of t is 8 e power minus 3t minus 2 cosine 2t plus 3 sine 2t. And so we saw how easier our life is now that we are using Laplace transforms for solving these initial value problems. Okay, let us solve the next example in a similar vein. The equation given to us is y double prime minus 3y prime plus 2y equals e power minus 4t, and the initial values given to us are the value of y at t equal to 0 is 1 and the value of y prime at t equal to 0 is 5. Again, we start by taking the Laplace transform of both sides. Laplace transform of y double prime minus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y is equal to Laplace transform of e power minus 4t, and this will be square y of s minus s y of 0 minus y prime at 0 minus 3 s y of s minus y at 0 plus 2 y of s equals 1 by s plus 4. And now if you collect terms on the LHS, ys times s square minus 3s plus 2 y at 0 is 1 y prime at 0 is 5 plus 3 times 5 is equal to 1 by s plus 4. Sorry, y at 0 is 1 and not 5. This implies fs times s square minus 3s plus 2 minus s minus 2 equals 1 by s plus 4. Fs times s square minus 3s plus 2 equals 1 by s plus 4 plus s plus 2. Plus s times s plus 4 is s square plus 4s plus 2s plus 8, which comes out to be s plus 4 times s square plus 6s plus 9. And which finally gives us y of s equals s square plus 6s plus 9 by s plus 4 times s square minus 3s plus 2. Can we simplify or factorize s square minus 3s plus 2? S minus a s minus b. Yes, we can. This will further simplify to s square plus 6s plus 9 by s plus 4 s minus 1 s minus 2. Okay. Now we must uh, decompose this into partial fractions. So y of s equals s square plus 6s plus 9 by s plus 4 s minus 1 s minus 2 equals a by s plus 4 plus b by s minus 1 plus c by s minus 2. And let us try to compute all of these coefficients by the cover-up method which we have practiced. So a is equal to s square plus 6s plus 9 by s minus 1 s minus 2 evaluated s equals minus 4, that gives us 16 minus 24 plus 9 is 1 by minus 5 times minus 6 is 30. B is s square plus 6s plus 9 by s plus 4 s minus 2 evaluated s equals 1. This gives us 1 plus 6 plus 9 is 16 by 5 minus 5 or minus 16 by 5. C is equal to s square plus 6s plus 9 by s plus 4 times s minus 1 evaluated at s equals 2. This becomes 4 plus 12 16 plus 9 25 by 6 times 1 25 by 6. And so we obtain y of s is equal to 1 by 30 by s plus 4 minus 16 by 5 by s minus 1 plus 25 by 6 by s minus 2. And we are originally solving for the function small y of t, which we know is which is the Laplace inverse of capital Y of s. Thus, y of t can be obtained by taking the inverse Laplace transform of these functions. So 1 by 30 by s plus 4 minus 16 by 5 by s minus 1 plus 5 by 6 by s minus 2. And from the properties of the transform, this becomes 1 by 30 the inverse of 1 by s plus 4 minus 16 by 5 inverse Laplace transform of 1 by s minus 1 plus 25 by 6 times the Laplace inverse of 1 by s minus 2. And if we are to find these inverses individually, first one becomes 1 by 30 Laplace inverse of 1 by s plus 4 is e power minus 4t. 16 by 5 1 by s minus 1 is e power t. 25 by 6 times plus inverse of 1 by s minus 2. This becomes e power 2t. And so the solution to the given non-homogeneous ordinary differential equation is y of t equals 1 by 30 e power minus 4t 16 by 5 e power t plus 25 by 6 e power 2t. And I see that we have also reached the end of our time for this session. So I'm keeping the session open for a few more minutes in case there are any doubts. Since there are no questions, we will close this session now. Thanks for tuning in to week 4 of the live sessions for the course on computational science and engineering. And it is my fervent hope that these sessions are helping the participants in solving the assignment questions and on a broader level in improving their understanding of the concepts that are being discussed in the course. And well, thanks for tuning in. I hope to see you again next week. Thank you.